Previously, we have discussed Sommerfeld's quantum theory by considering a free electron gas in one-dimensional potential box. And the concept of free electron gas in one-dimensional potential box is applicable for the one-dimensional crystals. But actually when we talk about crystal, the actual structure of crystal is always three-dimensional. The one-dimensional crystal and the two-dimensional crystals are only the theoretical aspect. So that description was not very appropriate. Okay. The actual situation is what? Since crystals are three-dimensional, so if we assume that the free electrons of the metal are confined within a three-dimensional cubical potential box, then the theory developed will be more appropriate in discussing the properties of metals. Okay? So today we are going to see this proper problem. And in this problem, first of all, we will discuss the basic theory of free electron gas in a three-dimensional cubical potential box. Actually, this problem is also studied in quantum mechanics, but when you will find it in the playlist of quantum mechanics of my channel, I have not provided it. I have already discussed the particle in one-dimensional potential box or potential well, but 3D potential box I have not discussed. So this is also for quantum mechanics. So this concept will be equally important for writing the answer of question in quantum mechanics and also in this solid state physics. So this first lecture is meant for the fulfillment of the requirement of quantum mechanics. Actually, when you study this problem in quantum mechanics, your aim is to find the energy eigenvalues and the eigenfunctions when there is a free particle in a three-dimensional potential box. Okay? So in this lecture, first of all, we will see it. So let us see this figure. I have shown in this figure a cubical box whose side length or edge length is L. Okay? And the three mutually perpendicular axes OX, OY and OZ has been taken along the three edges of this cube. Okay? And we consider that there is a free electron. When you say free electron, it means the electron is force free, and we assume that this is confined within this box. Okay? According to Sommerfeld's theory, when we talk about the free electron of metal, that free electron moves inside the surface of the metal freely because we neglect mutual interaction of electrons in this model and also with the positive ions. So electrons are actually treated as free. Okay? In fact, in his model, Rutherford has also assumed that the potential, that is potential energy you can say, inside this box is uniform, and for simplicity it is taken 0. Okay? But outside of this box or at the faces of this box, this potential abruptly rises to infinity, and so that you can say that the electron is confined within the box, it cannot pass or it cannot escape through the walls of the box, because at the wall the height of the potential barrier is infinite. Okay? So in this condition, how the potential function is defined, you can see it here. This potential function V, which will be a function of the three space coordinates x, y, z, that is equal to 0 in this range when 0 is less or equal to L and 0 is less or equal to Y and this is less or equal to L, and similarly 0 is less or equal to Z and this is less or equal to L. It means when you talk about inside the box, then potential field is 0. But outside of this box is this potential infinity. So this is the potential, how the potential varies in this region. Okay, inside the box, throughout the potential is 0, and outside of the box it is infinity. And since the potential at the surfaces is infinity, that's why electron cannot escape through the surfaces. Okay. Now you also know, if we talk about a free electron, then you know, since potential energy is the energy of interaction, but we are talking about a free electron in Rutherford model, so definitely the free electron in Rutherford model will have a zero potential energy. So V is equal to 0 in this case. Since potential energy of this electron is 0, so can you say what will be its total energy? You can easily say, since total energy is the sum of kinetic and potential energy, but since potential energy is 0, so definitely the total energy of this electron will be simply equal to its kinetic energy. So E is equal to Ke, and you know, for the non-relativistic motion, here the electron inside the box is also considered in a non-relativistic motion. When you say non-relativistic motion, that means the motion at a speed much smaller than light. And you know, if the motion is non-relativistic, then expression for kinetic energy is half mv square. Okay, and you can write this expression as mv whole square over 2m. But what is this mv? You know, mv is p, which is called linear momentum of the electron, and so the total energy E will be simply equal to p square over 2m. And so you can also say that this p square will be equal to 2me, 2m, where E is the total energy, or you can also say it is kinetic energy, because here total energy is equal to kinetic energy. Okay. Now you can also see how this potential varies. You can see that this potential is a function of position coordinates or space coordinate x, y, z only. It is completely independent of time. So if you will treat this problem quantum mechanically, you will have to think about the Schrodinger equation. You have to set up Schrodinger equation for this particle, that is this free electron, and you have to solve that very equation to get the energy eigenvalue and eigenfunction. But since potential function is space dependent only, not time dependent, so we must think about the time independent Schrodinger equation. Okay. So now write the three-dimensional time independent Schrodinger equation, which is given like this. This is this is Laplacian psi plus 2m over h bar square e minus v psi equal to 0. But you know, the Laplacian operator del square, this is equal to, in Cartesian coordinate it is equal to del 2 by del x square plus del 2 by del y square and plus del 2 by del z square. So this equation can be written as del 2 psi by del x square plus del 2 psi by del y square plus del 2 psi by del z square. This is instead of this Laplacian psi. Okay. But V is equal to 0, so the second term will be 2me over h bar square psi equal to 0. But you have just seen that in case of a free electron, this 2me, you have seen this is equal to p square. So instead of this 2me, we can write p square. So Schrodinger time independent equation in 3 dimensions becomes del 2 psi by del x square plus del 2 psi by del y square plus del 2 psi by del z square plus p square over h bar square psi equal to 0. Here p, this is linear momentum of our electron. Since momentum is a vector, so if your aim is to write down it in terms of its rectangular components, you can write that this p vector is equal to pxi plus pyj plus pzk. Here px, py, pz are what? These are the x, y and z components of this linear momentum vector. And so, the square of the modulus of this linear momentum p square will be equal to p square plus px square plus py square plus pz square. So in this Schrodinger equation, at the place of p square, you can equivalently write this much. That is, p square can be replaced by px square plus py square plus pz square. So now the time independent Schrodinger equation becomes del 2 psi by del x square plus del 2 psi by del y square plus del 2 psi by del z square plus px square plus py square plus pz square over h bar square times psi equal to 0. Okay, this is Schrodinger time independent equation. Now you can see here the wave function psi or the eigenfunction psi is a function of 3 independent variables x, y, z. That is, psi is equal to psi of x, y and z. And it is a partial differential equation of second order, where our function psi is a function of 3 independent variables. So definitely, if you will think about the solution of this equation, how you can solve it. You have definitely done the course on solution of differential equation in mathematical physics, and you have an idea that such a partial differential equation of second order is solved by a proper method which is known as variable separation method. There are so many methods, but variable separation method is frequently used in solving the physical problem like this. Okay? And if you will apply the variable separation method, then you can see that since psi is a function of 3 independent variables, so we must express this function psi as a product of 3 functions which are separately functions of the variables x, y and z. So you can write that this psi is equal to capital X of small x, capital Y of small y, capital Z of small z. It means we are considering that psi is equal to x times y times z, where this capital X is a function of only one variable small x. Similarly, capital Y and capital Z are functions of a small y and a small z respectively. Okay, only. Now, psi is defined by the product of x, y, z. Now, use this value of psi in this equation, that is equation number 1. When you will put, see here, what will be this del 2 psi by del x square? Since you can see that psi is a product of x, y, z, and you know this partial differentiation, when partial differentiation will be done, only the function of x will be differentiated and function of y and z will be treated as constant. So y and z will be outside and the operator will be operated on capital X only. Okay? Since capital X is a function of a small x only, So this partial derivative can be written as ordinary derivative, because here capital X is a function of only one variable x, so there will be no difference between this partial derivative and this ordinary derivative. So the first term becomes yz times d2x by dx square. In the similar manner, what will be the second term and what will be the third term, you can write on this basis. So after substituting that very equation becomes like this: yz times d2x by dx square plus xz times d2y by ds square plus xy times d2z by dz square. Okay, and in last term psi has been replaced by xyz. Okay, now you can see in this equation variables are not separated, because in every term the functions of x, y and z are present. Here you can see capital X, capital Y and capital Z are present in first term, in second term, in third term and also in the fourth term. So variables are mixed, not separated. But our aim is to separate the variables. So you can use a very simple algebra to separate the variables. If you will divide this equation throughout by this product x into y into z, the variables will get separated. So let us divide this equation by x, y, z. You can see when this first term will be divided by x, y, z, you can see this yz divided by x, y, z. So yz will cancel out and only 1 over x will remain here. So the first term becomes 1 over x d2x by dx square. Similarly, in second term xz will cancel out and in denominator there will be only y. So the second term will be 1 over y d2y by dy square. And in third term xy will cancel out. xy are divided by xyz. So xy will cancel out and 1 over z will left here. And so the third term is 1 over z d2z by dz square. And in the fourth term, completely this product x, y, z will cancel out. And so the fourth term is this much: px square plus py square plus pz square over h bar square, and that is equal to 0. So now you can see that the first term is only a function of x, you can see. The second term is only a function of y, and this is only a function of z. Okay, and the fourth term can be broken into x, y and z components. So now the variables are separated. Now again you know that the three coordinates x, y, z are actually known as independent variables. They are completely independent from one another. Okay. So for all values of x, y and z, this equation 3 will hold only when each part of this equation for a particular variable vanishes separately. So I have mentioned it here, you can see, as the three coordinates are independent of each other, we can separate this equation 3 into 3 independent equations, each being a function of one coordinate only. So writing for the x coordinate or terms which will be a function of x, what will be your equation? This will be 1 over x times d2x by dx square plus px square over h bar square. Here from the last term we take px square over h bar square, and that's equal to 0. Now if you will multiply this equation by capital X, your result will be what? This will be d2x by dx square plus 1 plus px square over h bar square x equal to 0. Okay. Now you can see in the similar manner when we will write the equation for in terms of y and z, our equation will become like this. This is d2y by dy square plus py square over h bar square y equal to 0, and d2z by dz square plus pz square over h bar square z equal to 0. Now you can see all these three equations, that is equations obtained in 4a, 4b, these are the standard ordinary differential equation of second order. And the form of this equation shows, you have definitely studied this equation in your course on mathematical physics, that the solution of these equations, that is the solutions x, y and z, are oscillatory functions. These equations will have oscillatory solutions. So its solution may be written either in terms of like e to the power plus minus I px over h bar times x or in terms of sine function or cosine function or a combination of sine and cosine function. So the well-known solution of these equations you can write now. So solution of this equation 4a, you know, this is written as x of x equal to ax times sine px over h bar times x plus bx cos px over h bar x. Okay, this is solution of equation 4a. Similarly, solution of equation 4b can be written as y of y equal to ay sine py over h bar y plus by cos py over h bar y. Okay. And the solution of this equation 4c in the similar manner, you can write z of z equal to az times sine pz over h bar z plus bz times cos pz over h bar z. Here actually, you know, these ax, ay, az, bx, by, bz, all are arbitrary constants. Okay. And actually, now to get the arbitrary constants or the integration constant involved in these equations, we will have to use the proper boundary condition. And for proper boundary condition, let us see first of all this figure. This figure. You know, inside this box there is electron, and outside of this box there is no electron, because at the surface potential is infinite, and so electron cannot escape through the surface of this box. Okay. So x, when x is less, x is, sorry, at x equal to 0 and x equal to L, these are the boundaries. Okay. Similarly, y equal to 0, y equal to L, these are boundaries. And you know, wave function has a proper property that at any boundary its value is continuous. Its value is continuous. Okay. As the probability of finding of electron just outside of the box is 0. Okay. So when x is greater or equal to L, or x is less or equal to L, in both of these conditions psi will be 0, because the probability of finding of electron outside of this box is 0. And so the probability density is mod of psi square 0, and mod of psi square 0 means psi 0. Okay. So at the surfaces or at the boundaries, the wave function or the eigenfunction psi must vanish. Okay. So our boundary condition is this capital X will be 0 when a small x is either 0 or L. It means when x is 0 and x is L, in both conditions this capital X will be 0. Similarly, capital Y will be also 0 when a small y is 0 or a small y is L, and this capital Z is 0 when a small z is 0 and a small z is L. Okay? Now we will utilize these boundary conditions to evaluate the constants Ax, Ay, Az, Bx, By, Bz. Okay? Actually from this the constant Bx, By, Bz will be evaluated, and after that we will obtain the other constant by utilizing the normalization condition. So now let us first of all apply this condition. When x is small x is 0, then this capital X is 0. We apply this boundary condition on this equation 5a. What you will do? In RHS, we will put a small x equal to 0 in both terms, and the boundary condition says when a small x is 0, this capital X is 0. So applying this condition, we can write 0 is equal to Ax times sine 0 plus Bx times cos 0. But you know, sine 0 is 0, so the first term is 0, and so first term is 0, and cos 0 is 1, so second term is Bx. Okay? And your LHS is 0. LHS is 0. So this result shows that constant Bx is equal to 0. So applying this boundary condition, we have obtained the value of the constant Bx, which is found to be 0. And since Bx is 0, so this equation 5a now will be what? This will be x of x equal to Ax times sine Px over h bar times x. Okay? So now write this. You can see our equation 5a now becomes x of x equal to Ax times sine Px over h bar times x. Okay? Now on this equation 6, we will apply the boundary condition that when x is equal to capital L, see it here, then capital X is again 0, see it here. So in RHS of equation 6, when this small x will be replaced by capital L, then in LHS this capital X will be replaced by 0. So do it. What will you get? You can see 0 is equal to Ax times sine Px over h bar into L. Okay? But you know that this Ax is not 0, because when Ax will be 0, then for all values of x, this capital X will be 0. And if capital X is 0, then psi will be 0. And psi is 0, if psi is 0 everywhere, it means electron is nowhere. This is completely unphysical because we know electron is present inside the box. But if we will take Ax0, then our result will be electron is even not inside the box. Electron is nowhere. Okay? So that is unphysical. So we must say that this constant Ax cannot be 0. And as Ax is not 0, so definitely this second factor sine Px over h bar L must be equal to 0. And you know, the general value of theta when sine theta is equal to 0, you know, the general value of theta is n pi. So here, at the place of theta, there is Px over h bar into L. So you can say that Px over h bar into L is equal to nx in nx pi. Instead of n, here I have written nx. But you know, when sine theta is 0, theta is n pi, and in that condition, what is n? N is 0, 1, 2, 3, and so on. But here you can see I have written that n is not, this nx is not equal to 0. This thing I have also explained in case of particle in one-dimensional box. Why I have taken nx not equal to 0? Only this integral value 1, 2, 3, 4, so on are accepted here. Because you know, if we will take nx is equal to 0, okay, in that condition you will see here in this equation that this x, capital X will be 0 for any value of x. And again the same problem will arise. When capital X is 0, psi will be 0 because psi is x, y, z. And if x is 0, then psi will be 0 for any value of a small x. That means electron is nowhere. But electron is present inside the box. So this value of nx, that is nx equal to 0, is restricted. You can't take it. Mathematically it is all right, but physically in this present situation we cannot take nx equal to 0. Okay? And so you can say that this px over h bar will be equal to nx into pi over L. Okay? Now let us substitute this value of px over h bar in this equation 6, and then you will get the function capital X. So this capital X is equal to ax times sine nx pi over L times x. Okay? This is the value of x. Our solution of this equation, which I have written in this equation 4a. This is its proper solution. Now in the similar manner, you can see the form of equation 4b and 4c are same as that of 4a. The only difference is what? The function capital X, at the place of capital X there is capital Y and capital Z. At the place of px there is py and pz. Okay? So in the light of the above results, now in this case you can apply the boundary conditions which I have mentioned here and here. Applying these boundary conditions in the same manner, you will see that as bx was found to be 0, in the similar manner by and bz will be also 0 in the same way. I have not done the algebra, but you can do it. And after that you have applied the another boundary condition and you have obtained this result, px over h bar equal to nx pi over L. Similarly here you will get py over h bar equal to ny pi over L, and pz over h bar is equal to nz pi over L. But here these quantum numbers ny and z will be also have like this value 1, 2, 3, 4 and so on. Okay? And the solution of those two equations can be directly now written on the basis of this equation number 7. Okay? Only this capital X will be replaced by y and z, the subscript x will be replaced by y and z, and this small x will be also replaced by y and z. And so you can write that the solutions are y of y equal to ay times sine ny pi over ly, and z of z equal to az times sine nz pi over L times z. But you have seen the complete wave function psi. This is the product of these three wave functions x, y and z. So now the solution of our Schrodinger time independent equation, which is psi, is given like this. Let us multiply these three equations, that is equation 7, equation 8 and equation 9, where the values of capital X, capital Y and capital Z are defined. Let us multiply it. This will be ax times ay times az times sine nx pi over lx times sine ny pi over Ly times sine nz pi over Lz. Now since Ax, Ay and Az, all these three are constants, so their product will be also a constant. And we have assumed that the product of Ax, Ay, Az is equal to A. So finally, you can write the eigenfunction in this way: psi of xyz is equal to A times sine nx pi over L x times sine ny pi over L times y sine nz pi over L z. This is the eigenfunction. But this constant A, which is actually called the normalization factor or normalization condition, this is not known till time. And you have an idea that if your aim is to find this normalization factor, you must apply the normalization condition followed by our wave function. In other way, you can also say that the probability or density of finding of a particle is mod of psi square. So the probability of finding of particle in an elementary volume dx, dy and dz, this will be this density guna this elementary volume. But the finding of particle inside the box is definite. It is not a probability, it is a certainty. So if you will obtain the total probability of finding of the particle inside this cubical box, that will become a certainty, that will be equal to 1. And that's why when we will integrate this for the entire cubical box, then our result will be equal to 1. This is also called normalization condition. Okay. Here, x varies from 0 to L, y also varies from 0 to L, and z also varies from 0 to L. So the limits of the three integrals are 0 to L. Okay. Now, what is the value of psi? You can see psi is since real, not complex. So its square will be simply a square sine and a square of all these signs. Okay, but a square is a constant factor, so take it outside of the integral. So this is a square times integral 0 to L sine square nx pi over Lx dx integral 0 to L sine square ny pi over Ly dy times integral 0 to L sine square nz pi over L z dz, and that's equal to 1. And you have seen the evaluation of this integral in case of particle in one-dimensional box, and you can do it. When you will integrate, you will see that the first integral is L by 2, second integral is also L by 2, and third integral is also L by 2. So this is in fact L cube over 8. So a square is equal to 8 over L cube, and that's why a will be equal to a square root of 8 over L cube. Here actually L cube, you can say this is equal to tau, and this is volume of the box. Volume of the box. You can also say at the place of this L cube you may write tau, which is volume of the box. Okay. So in this way we have calculated the value of this normalization factor. Now let us substitute this value of A in this equation 10, and after that you will get the normalized eigenfunction. So what is the normalized eigenfunction? You can see psi of xyz, which is equivalently written as psi of vector r. R is the position vector which represents xyz, and that will be equal to a square root of 8 over L cube times sine nx pi over Lx sine ny pi over Ly sine nz pi over Lz. So you can see this eigenfunction depends actually on the three quantum numbers: In case of particle in one-dimensional box, we have seen there were only one quantum number. There our result was psi equal to root over 2 by L, sine n pi x over L. This was our result. Okay. But here there are three quantum numbers nx, ny and nz. So the values of this psi for a given value of x, y and z will also depend on the three quantum numbers. Okay? And this will be actually discussed in case of degeneracy later on. So in this way you have calculated the normalized eigenfunction or eigenstate or wave function. Now our aim is to evaluate the energy eigenvalues. What are the values of the energy of this electron confined within this potential box? Now we will calculate it. And for this you can see the result which we have obtained earlier. You can see this result. We have obtained that Px over h bar is nx pi over L and Py over h bar is ny pi over L and Pz over h bar is nz pi over L. Actually, using these three results, you can find the value of Px, Py and Pz. And you can see Px is this much, Py is this much and Pz is this much. Okay? But we know that the square of the magnitude of momentum p square, this equal to px square plus py square plus pz square. Have you seen earlier? Okay. Now let us substitute the values of px, py and pz here. You can see in the values of px, py, pz, the factor pi h bar over L is a common factor. Okay, so you can take pi square h bar square over L square as a common factor, and the remaining terms will be what? The remaining terms will be nx square plus ny square plus nz square. Okay, but we have seen earlier that this p square is equal to 2me. So this p square will be now replaced by 2me. But at the place of e, I have written e, nx, ny, nz. Here the quantum numbers nx, ny, nz has been written as subscripts of e. Why? Because in this case, the value of the energy E depends on the three quantum numbers. So, showing the dependence of energy eigenvalue on the quantum numbers nx, ny, nz, I have actually written these nx, ny, nz as a subscript of E. Okay? So, 2m E nx, ny, nz is equal to this much. And so, the energy eigenvalue when the quantum numbers are nx, ny and nz, that is written as E nx, ny, nz, that will be equal to pi square h bar square over 2ml square times this much, nx square plus ny square plus nz square. Actually, in case of the one-dimensional box, you have seen the expression was like this. This was pi square h bar square over 2ml square times n square. This was the result. But here at the place of this n there is nx square plus ny square plus nz square. Since nx, ny, nz has discrete values, so you can see that in this case too, the energy eigenvalue of the electron will be discrete. It means the energy of electron inside this three-dimensional potential box are not has not continuous value, but the energy will have discontinuous or discrete values. Okay? Discrete value. Now, one thing here you can see from this result A. If you take nx equal to 0, but ny is not equal to 0, nz is not equal to 0, then you can see if nx is 0, then this first sign factor, sin nx pi by lx, that will be sin 0, and sin 0 is 0, and due to that psi will be equal to 0. In the similar manner, you can say that when any quantum number, either nx or ny or nz, is equal to 0, then the wave function will become 0. And if wave function is 0, that means electron is nowhere. Electron is not present in this region. But that is completely unphysical, because we know electron is present inside the box. So this result shows that the three quantum numbers nx, ny, nz can be never 0. Nx, ny, nz can be never 0. And I have also told you this very fact in the beginning. So you can't take nx equal to 0, you can't take ny and nz equal to 0. So what is the possibility for the least values of these three quantum numbers? The least values in that condition will be simply 1. So nx, ny and nz equal to 1, this will be the least value of these three quantum numbers. And when nx, ny, nz will have least value, the energy eigenvalue will be also lowest. Okay, and that is called ground state energy or 0 point energy. So when you want to find the ground state energy or 0 point energy, then you have to take these three quantum numbers equal to 1. Okay? And taking these three quantum numbers equal to 1, what will be the energy eigenvalue, which is called lowest energy or ground state energy or 0 point energy? Symbolically we write it E111, and that will be, you can see this result, this will be pi square h bar square over 2ml square, and 1 square plus 1 square plus 1 square. So this is simply 3 times pi square h bar square over 2ml square. This is the ground state energy of the electron, or the lowest energy of the electron, or 0 point energy of the electron inside the box. So energy of electron inside the box is never 0. At least this much energy the electron will have when it is inside this three-dimensional potential box. And since it is the least energy, so it is called the ground state energy or the 0 point energy. Even at 0 Kelvin temperature, this much energy our electron will have. Okay. Now, in fact, we will talk about degeneracy, and in this regard, we have calculated the value of the 0 point energy or the lowest energy. Now, let us see this expression for the eigenfunction. In ground state, what will be the value of this eigenfunction? So, ground state eigenfunction, if your aim is to found, then you can put nx, ny and nz equal to 1. So you can see the ground state eigenfunction psi 111, this will be a square root of 8 over L cube and sine pi x over L times sine pi y over L times sine pi z over L. So what are you seeing here? Corresponding to this ground state, the energy eigenvalue has one value E111, and corresponding to this energy eigenvalue, there is only one eigenstate, only one eigenfunction or wave function. In other words, you can say corresponding to this energy eigenvalue 1 E111, there is one and only one eigenfunction psi 111. And you know, the number of eigenstates or number of quantum states corresponding to a given energy eigenvalue is called degeneracy. Since here this energy eigenvalue, corresponding to this energy eigenvalue, there is only one eigenstate, so this state is called non-degenerate. This state is called non-degenerate. It means the ground state of the electron inside a potential box is non-degenerate. Okay. Now let us think about the first excited state. What will be the quantum numbers for the first excited state? When you will take any one of the quantum numbers equal to 2 and the remaining 2 equal to 1, then you will get the first excited state. So in case of first excited state or next higher energy state, there will be 3 sets of quantum number, and those sets will be 2, 1, 1. It means nx is 2, ny and nz are 1. The another set will be 1, 2, 1. It means nx is 1, ny is 2, and nz is again 1. And third set will be 1, 1, 2. It means nx and ny are 1, but nz is 2. Okay. But for these 3 sets of quantum number, you can see the energy eigenvalues will be same. They are not different. When you will find it, at the place of this nx, ny, nz, you have to put one of the number 2 and remaining 2 equal to 1. And so your result will be this much. This is 6 times pi square h bar square over 2ml square. Okay. So the first excited state has this much energy. Okay. Now let us find the eigenfunction corresponding to these 3 sets of quantum numbers. Let us find. So psi 211, this will be 8 over L cubed square root times sine 2 pi x over L, sine pi y over L, sine pi z over L. Okay. Again, psi 121, psi 121. What will be this? This will be a square root of 8 over L cube, sine pi x over L, sine 2 pi y over L, sine pi z over L. Okay. And for the third set, psi 112, this will be 8 over a square root of 8 over L cube, sine pi x over L, sine pi y over L times sine 2 pi z over L. So what are you seeing here? Are these 3 eigenfunctions equal? Answer is no. They are different. But these 3 eigenvalues are same. So for the first excited state, there is only one energy eigenvalue, but corresponding to this one energy eigenvalue, there are 3 quantum states in which electron will be found. Since corresponding to one energy eigenvalue, here there are 3 quantum states, 3 eigenstates or 3 eigenfunctions. So this energy state is called threefold degenerate. Its degeneracy is 3. What is its degeneracy? It is 3. Okay. So degeneracy of this first excited state is 3. So I have mentioned the important points here. You can see a free electron in a cubical box is thus a case of degeneracy. The lowest energy state, which is 111, that is non-degenerate. We have seen The first excited state is threefold degenerate. You can see it here. Next higher energy state, if you will take 2, 2, 1, then again you will find that this is also threefold degenerate. Okay? But the next higher state, that is the this 2, 2, 2, when nx is 2, ny is 2, nz is 2, then you will again see that this state is non-degenerate. So what's the conclusion? We can conclude that when all nx, ny and nz are not equal, then that energy state will be degenerate, and degeneracy is fixed, that will be equal to 3. But if nx, ny, nz, all these three quantum numbers are equal, that is nx, ny, nz all are 1, all are 2, all are 3, all are 4, all those energy states will have no degeneracy, they will be non-degenerate. So you can say that in case of particle in a three-dimensional box, for the state nx barabar ny barabar nz, all these states are non-degenerate. But if any one of the quantum number is different, then that state has threefold degeneracy. This is a very important fact and very important for your objective questions. Okay? So I think you have clearly understand the basic concept or basic physics of this free electron inside a three-dimensional box, particularly regarding the energy eigenvalue and its calculation, the eigenfunction and its calculation, and how we can discuss the degeneracy in this case. Okay? So definitely you have enjoyed the lecture as I hope. So thank you very much.